don't understand. Yeah. Like there is a great golf course to the thick, like so. It's so bad. That one's except I got a 95. I'll see really. Now would you like off the mic? You and like this. I really kind of like see like that's what I'm saying. We're gonna go. Yeah, that's what it's just not. And so I'm okay, so I'm gonna redo the front. No, it's not.
All right, let me know if you don't have access review packets. Yeah. Just like that.
It's classic.
You guys listen?
They can make it free. I think like especially if they get in, like the government.
All right, let's start at page 2 in your packet.
Like just go and they look for
Okay, so an object's position is given by f of p. We see that trig function with that shorthand way of writing the exponent, so we want to definitely rewrite it with that exponent outside the set of brackets. Function is continuous and differentiable in the domain. And f of t is given in meter. Find the average velocity. So average velocity is change in position over the change in time. So we don't touch the velocity function as we are asking, even though we see the word velocity in the description, average velocity is change in position over the change in time. So no calculus here. We're just plugging in and finding slope. So I want you guys to try this by hand. Don't plug this in the calculator. Okay, give that a try. See if you can. You have your endpoints there, 0 and 2 pi. So All right, secant of 0, same thing as 1 over cosine of 0. We know cosine of 0 is 1, so 1 over 1 is still 1. Cosine, secant of 2 pi is related to cosine of 2 pi. Cosine of 2 pi is also 1. Flip that 1, we still get 1, so. Oops, sorry. My bad. I forgot to include that 1/6 here. Try that again. The first one is 0 over 6, that's fine, but the second one is 2 pi over 6, which is not the same thing as just 2 pi. Then all right, so secant of pi over 3 is related to cosine of pi over 3. We know cosine of pi over 3 is 1/2. So if I flip 1/2 to get to secant, I get 2. So 2 times 8 is 16. Okay, so then my average velocity is just the change in position divided by the change in time. So 16 minus 2 divided by 2 pi minus 0. Part B. Part B says, at what time t does the instantaneous velocity equal the average velocity? So anytime we see this description, instantaneous rate of change equaling the average rate of change, instantaneous velocity equal the average velocity, this is an indication that they're describing mean value theorem to us. Right? Instantaneous velocity is the derivative component. Average velocity is the slope component. So typically we think of mean value theorem as this formula, right? Average rate of change equaling the instantaneous rate of change. And now we can adapt this to, for this particular problem, which is the change in velocity. Which is change in position over change in time, equaling the velocity function. We have this piece, right? We already know that we can guarantee that somewhere this particle is going to have this is going to reach this average velocity of 7/2 pi. And we can just set the velocity equal to this. But it's only asking us to set it up. We're not asked to solve it. So we'll find f prime, or call it the velocity function. So we set the derivative equal to our average velocity. So here's my position function again. And we definitely have to go through chain rule here, right? There's an outside, inside portion we have to go through. So we take care of outside's derivative, 6 brackets squared. Times inside's derivative, secant of u becomes secant u tangent u times u prime. So we're just going to set up mean value theorem. So we have our derivative. We have our average velocity. And we're just setting them equal to each other. We're not going to solve it. That'll be too much to do. So this one is only asking us to set it up. So it looks like the sixes can cancel out. I can merge the secants together to make it secant cubed. So if we were to solve for t, then we will be able to find the moment in time when this particle is going to reach this exact velocity of 7/2 pi. Part C, what is the instantaneous velocity of the object when t equals pi seconds? So we have the velocity function, which is our derivative. So just plug pi into your derivative and see what that gets you. Same thing with part D. We're just plugging in. All right, we know secant related to cosine. Cosine of pi over 6 is √3/2. So secant must be the reciprocal of that, right? So if cosine is √3/2, then secant would be 2/√3. Tangent of pi over 6 would be 1/√3. Sine over cosine, or sine over cosine is tangent. So 2 cubed is 8. Here, we're essentially doing root 3 to the 4th power, right? Because there's 3 root 3s here. There's 1 root 3 here. 2 root 3 gives me 3. And so 4 root 3s will give me 3 times 3, which is 9. So just practicing with our unit circle values here, right? All right, try part D. Same process. You're just plugging in a different t value into the derivative. Pi over 3, secant of pi over 3 is cosine of pi over 3 is 1/2. So flip that, we get 2 over 1. Tangent of pi over 3, root 3 over 1, or just root 3. Two cubed is 8. Okay. Find the equation of the tangent line to f of t at 2 pi. So we have the slope at 2 pi. We should need the y value at 2 pi. So we'll plug 2 pi back into the original equation to get the y value, and then we'll do point slope form. Okay. Again, secant of pi over 3 is 2. 2 cubed is 8. 8 times 2 is 16. So there's my ordered pair. And there's my slope. I'm using t here because that's the variable that we started with. Any questions? Page 2. Okay, let's go to page 3. We'll skip the first 3 problems, not worry too much about solving these trig functions, but maybe we can use the space here just to practice with our new set of derivative rules. But I just want to focus on the first column, arcsine, arctangent, and arcsecant. So see what you remember. They all involve u prime and they all involve 1 and u squared. See if you can remember how they're organized within each derivative rule. And I'm only worried about the first column because that if you can do the first column, then the second column should be easy with the negative versions. Once you get done with this, then we're going to try number 4. So number 4 should feel like a little bit of review from your trig derivative quiz. Arcsine, arctangent, arcsecant, check your derivative rules. See how you did. Okay. Let's try number 4. So number 4 says, write the equation of the tangent line at 3, -1. So we just have to find slope through the derivative and then point slope form. Right? Find the equation of tangent line to the curve at 3, -1. So we have to find the derivative, and the derivative, we can plug in our order pair to get the slope and then point slope. All right, looking at this equation here, what's involved if we want to find the derivative? Implicit. Okay, you can probably see multiple y's kind of mixed into the equation. Okay, what else? Product rule, yeah. F prime g plus f g prime here. And also a little bit of chain rule here. You know, sine of u is cosine of u times u prime. Cosine of u is negative sine of u times u prime. Okay, so go ahead and try that. I'll work alongside you guys as you guys try it. Okay. We know that in our derivative step, we're expecting two dy dx's, right? We have two y variables to begin with, so we should have two dy dx's pop up. So the first one is going to pop up here, and the second one will pop up when I go through a product rule here. Any questions here? Now, you may feel like you have to rearrange it and solve for dy dx, but we can save a little bit of algebraic steps here because this is only asking, we only care about finding slope. So we don't have to worry about isolating dy dx in terms of x and y. So to save a little bit of time, we can just go ahead and plug in 3 and -1 directly into this unreduced derivative, because a lot of things will cancel out and clean up, and we can, after we replace all the x's and y's with 3 and -1, then we can rearrange the dy dx, and it should be a lot easier to get dy dx in terms of a slope value because we have less variables to keep track of. So I'm just going to save a little bit of time here. Go ahead and plug 3 in for x, -1 in for y, clean up, and we should be able to get that dy dx slope a little faster. Cosine of 3 pi, if you don't recognize 3 pi, you can always subtract 2 pi to get it into an interval that you're more familiar with. So 3 pi minus 2 pi is pi. 3 pi, same thing as pi here. So cosine of pi is -1. Gives me -1 times pi, which is negative pi. Cosine of negative pi, if you don't recognize negative pi, you can add 2 pi to it. We get cosine of pi, which is -1 as well. So two negatives. Oh, sorry, I messed up. Sine's derivative is cosine. Cosine's derivative is negative sine. Sorry. So sine of negative pi is same thing as sine of pi. Sine of pi is 0, so that's nice. Wipes this whole thing out. So only have to worry about this dy dx. Okay. So I'm gonna move this -6 over to the other side here. 6 minus pi is equal to 9. Okay. A lot less to keep track of because a lot of things collapse after all the variables are gone. So divide both sides by 9, and that's our slope. Right, so we have our point. We have our slope. Now point slope form.
Sine turns loud.
Why does Oh, this cancel out?
Yeah.
So negative pi, if you don't recognize negative pi, the same thing as adding 2 pi to this. So that becomes negative pi plus 2 pi is pi, right? And so sine of pi is just going to be 0. So 0 times pi times dy dx is going to be 0. So that's just this whole thing left out. Any questions? Okay, let's do a related rates problem. Next page, page 4. Number 5. Now on the test, the diagram will be drawn for you, so you don't have to worry about having to figure out how the diagram is drawn. So let me draw this out here. So y is traveling south. X is traveling east. So person Y is heading towards the intersection. The person X is moving away from the intersection. Eventually, we're going to have to figure out the rate of change of theta. So, but that's where theta is. So we'll let this represent our Y. Horizontal will be our X, and then our hypotenuse will be our Z. So part A is going to be a familiar related rates problem, Pythagorean theorem. Find the rate at which the distance Z between person X and Y is changing when Y is 10 meters from the intersection and X is 20 meters from the intersection. So Pythagorean theorem. Derivative, this is where all of our d over dt's will show up after we find the derivative of each term. Okay, let me list out all the variables involved. Okay, Y travels south and approaches the intersections at 2 meters per second. What do we assign that 2 meters per second for? Related to Y, but there's movement involved. d1 dt. Okay. Any adjustment we need to make with that 2 meters per second? Negative, right? Not because it's going south, but because this distance is decreasing, right? This side of my triangle is decreasing over time. So person X is traveling east, moves away from the intersection at 1 meters per second. So not because he's moving right, but because this distance is increasing over time. You want that rate to be a positive. So +1 for dx dt. Find the rate of the rate of change of z. So that's the unknown. And then when y is 10, x is 20, and then Pythagorean theorem can help us get to z. Right? It's not going to be a nice Pythagorean triple, so let's work this out. Ends up being 100 plus 400 is 500. Square root of 500. It's going to be 10 root 5. Okay, to find dz dt, we can put everything in. We get 40. So this ends up being 0. 0 over 20 root 5 is still going to be 0. So the reason why dz dt is 0, typically that's not going to be the case, is because maybe this distance was increasing, but then all of a sudden it changes to decreasing. So it just happens to be at that moment where that rate of change is going to stall for just that brief moment. So it's not, if it was any time before and after, we know z is going to be changing. It's not like the ladder problem where it's going to stay constant the whole time. It just so happens at this moment in time, the rate of change between x and y is 0 momentarily. Okay, part B. At what rates is the angle theta changing at this same moment? So typically, we want to take advantage of a side length that is a constant, so we can avoid quotient rule. But you're going to see some problems that may not always, like this one, where supposedly all sides are changing at any moment in time. So I want us to practice problems where we have to go through quotient rule. So let's use tangent. The reason that I want to do tangent is because we have information provided at the beginning involving x and y. So typically, we like to use the original variables in the problem, so that we can just have the direct data from the beginning of the problem. So we're trying to find d theta dt, but we're going to set up using the original variables x and y. There are no constants in this problem. Okay. We could use sine or cosine, but I want us to practice using tangent. Okay, so tangent's derivative is secant squared. D theta dt. Y over x, quotient rule. Okay, f prime g minus f g prime all over g squared. We have everything that we need from part A. But what's different about trig-related rates is we're going to have to build a second triangle to find the full replacement for that secant theta, or secant theta squared. Again, the biggest trouble students have when they get stuck is they're usually stuck trying to find theta. They don't know how to find theta, but we're not looking for theta, right? We're trying to find something to replace the entire secant of theta. Okay, so we're going to set up a second triangle to help us figure out how can we find the replacement for that secant theta. So I'm going to draw a second triangle here with all the numeric values filled in for this moment in time. X is 20, Y is 10, and Z is 10 root 5. So secant is reciprocal of cosine. Cosine is adjacent over hypotenuse, so therefore secant is hypotenuse over adjacent. Which I can reduce to be just root 5 over 2. And now I can take this and put it in place of secant, and I'm going to have to square it, right? Square my ratio here. Okay, so then I can square it, move it over to the other side. Remember, we're dividing by a fraction, and same thing as multiplying by the reciprocal. So here's my result of d theta dt. So -4 minus 10. Oops, sorry. X is 20, not 2. -40 minus 10, -50. And this gets me 5 over 4, which if I divide it over or multiply by the reciprocal, it gives me 4 over 5. And the rest I can just put in the calculator here. Okay, units of measure, your theta is always going to be radians, never degrees. So it's radians per time unit per second. Any questions? Okay, so tomorrow we'll do curve sketching and we'll do more related rates. Okay, all right, come get your phones.